Okay, so we're continuing on with this first order stuff, and I left I realized after I stopped the video, I left a negative sign off of something up here. The slope is negative k. So got it correct here, but then left off the negative sign up there. So fix that in your notes. So we've got the first order integrated rate law derived. We did some awesome calculus. We did an example of how this equation is used. It's really straightforward, just in terms of plugging the equation in. The next thing that we're going to talk about is something called half-life, because it relates to this concept of the integrated rate law. So at first, when we first start talking about half-life, it's going to feel like this doesn't really tie into anything, but trust me, it does. So you've probably heard of and used half-life before, maybe in biology. The half-life is defined as the amount of time that it takes for an initial concentration to decrease by half. And this number is used a lot in nuclear chemistry, when we're talking about radioactivity of a substance. We talk a lot about the half-life. How long does it take for the amount of this particular substance to be decreased by 1/2? Half-life is relevant here because it is calculated from the integrated rate law, if you think about it, because that's exactly what the integrated rate law is used for. Let's remind ourselves. So the integrated first order rate law is going to be the natural log of whatever our reactant is at time t, equal to negative kT plus the natural log of the initial concentration. And anytime a problem is asking us to calculate how much we have at a specific time, we're always going to be using our integrated rate laws. A half-life problem is asking us, how much do you have at a specific time? Half of how much time does it take? And so because of that, it is definitely related to the integrated rate law. So when we are trying to use the integrated rate law to do a half-life calculation, we are going to redefine some of these terms. When we are actually at the half-life of a reaction, we are going to write t, the time, we're going to call it t1/2, because we don't exactly know for sure. A lot of times we don't exactly know for sure how much time that is. Like, is it 110 seconds or is it 300 seconds? So we're just going to call it t1/2 for half-life time. And we're also going to say that our concentration of A at the half-life, so at t1/2, is equal to, by definition, 1/2 of our original concentration. So that's just coming from the definition of the half-life. So let's take these two terms right here, plug them into our integrated first order rate law. So instead of saying the natural log of A at time t, we are going to say the natural log of A at t1/2, and that is equal to negative k t1/2 plus the natural log of A initial. So we're just kind of getting this set up in terms of, half-life and thinking about half-life. So now what we're going to do is use this equality right here. And so we're going to say the natural log of 1/2 of our initial concentration of A, so that's our A at the half-life, is equal to negative k t1/2 plus the natural log of A at time 0. And then we're going to do some amazing algebra. So then we're going to go, let's move both of the natural logs to the same side of the equals sign. So we get natural log of 1/2 A at time 0 minus the natural log of A at time 0, and that is equal to negative kt1/2. And whenever you have, so one of the properties of a log is that if you have the log of A minus the log of B, that is equal to the log of A over B. So we're going to use that property, and we're going to say the natural log of 1/2 a at time 0 divided by a at time 0. So that's allowing us to combine the two together. That is equal to negative kt 1/2. Those a zeros cancel out, and we are left with the natural log of 1/2 equals negative kt 1/2. Oh, this is turning into such a beautiful equation. We can move the negative sign from the right side over to the left side. Natural log of 1/2 equals kt 1/2. And another property that we have of logs is the negative log of something, 1 over a, is equal to the log of a. So hopefully you're comfortable with your math. So now we can rewrite that as the natural log of 2 equals kt to the 1/2. We've really simplified this. And we're trying to solve this in terms of half-life, like as in what is the half-life. So here we go. The half-life is the natural log of 2 over the rate constant little k. Oh. And since we can actually plug that into our calculator, we can actually plug in the natural log of 2, simplify this even more. We're going to get t 1/2 equals 0.693 over the rate constant little k. And that is our equation for calculating the half-life for a first order reaction.